has the bones. Okay. Problem 4. Prove that the only connected sets of R. Alright, let me try to remember. Connected set. Connected if and only if. For all non-empty disjoint sets, A and B, satisfying E equals A union B, all non-empty disjoint sets there always exists a convergent sequence xn converging to x of xn containing one of A or B, and x is an element of the other. Interesting. If for all non-empty non-empty disjoint sets A and B there always exists a convergence sequence. That's kind of weird. The empty set. Intervals closed open finite and the set containing a single point. That's pretty spicy. Oh shit, I can't be playing copyrighted music. This always happens. Okay, alrighty. If and only if for all non-empty disjoint sets oh my god, I'm sick as a dog. For all non-empty disjoint sets A and B satisfying E equals A union B, for all non-empty, I think it's just like vacuously true. The capitalization on this is fucked up too. Well, I'll answer those questions both in a sec. I'm not seriously considering going back to LaTeX. I don't think I need a hole proof environment for this one. This one's just goofily true. Vacuously true by definition. Well, okay, so one argument for LaTeX is that LLMs are getting way better at doing it, especially for like simple assignments. Like this isn't crazy. There's no insane formatting or anything going on. And so what you can do is do your math homework on paper, which is for a lot of people like a lot more comfortable, and then take a picture and then just get like an LLM to turn it into LaTeX for you. So it'd be like you're not really even using LaTeX. And I know like a bunch of people in my class do that, and I did that for one assignment, but I don't know, it's like I prefer types. I like to handwrite things, and it's just it feels better. How do I learn to code? I mean, like I feel like you already know how to do that. That's one of those questions like you ask and you're like hoping the answer will be like something other than hard work. Which is fair, because hard work sucks. But yeah, that's all there is to it. Okay. Sets consisting of a single point. The singleton sets. I'm studying real analysis currently. Yeah, I am a math major. And a computer science major, actually. Okay. Sets consisting of a single point, the singleton sets. So, like 1 is connected. So, Conrad. So, the definition of connected is that any two non-empty sets, their union What is the definition again? Oh, convergent sequence in one, the limit in another. With an element in the other. Okay, the union of two sets. The set consisting of a single. If for all non-empty disjoint sets, A and B. But that's also got to be true, because if a set is a single point, you can't have disjoint sets. By the definition, you can't have so it's vacuously connected. Hey, Johnny's here, and it's really zen. Some OGs. You other guys before we're all weird. I'm not gonna lie. Plotzed. Yeah. I've never done it myself, but I'd like to learn more typed packages. It'd be worth looking into. Scatter plots, histograms, pie charts. Yeah, that looks pretty nice. It would be sick if someone would write like a Desmos to Typed plugin. Maybe I'll do that. Like where you, I don't know if that would be possible, but if you can extract like the JavaScript state of the Desmos window into like a plots diagram, and yeah, I've never really had to do this for like my homework. I guess if you were writing like a paper or something, then yeah, then it would be more interesting. It's crazy how much like work the types team does. Like I swear these guys are actual 10x developers. It's like 3 people that do the whole thing, and I want to read at some point. Not a data visualizer, yeah, but you could have like a function plot. Also, I think you can like data visualize. It's just like really hacky. Commutative diagrams. Whoa. Yeah, there's some paper by the types guys, like there we go. This is like the paper that types rests on. Well, an implementation of the paper, I guess. Maybe it's not linked. Does someone know what I'm talking about? Incremental. Through constrained. $3D game. Yeah. We had a project in high school to do that. To build like games in Desmos. It was cool. I don't think I have that account anymore, but no. I can't find this, but maybe it's on is there like a tech paper that this guy published? Separates words into syllables. No. I'll find it another time. Should be doing real analysis. Okay, so I think these first 2 are pretty easy. Now we're going to have to actually invoke the definition, which sucks. So, intervals, open, closed, and infinite. So an open interval set's connected if it's got two sets whose union who unionize together to make it, and one of those sets has got a limit and the other one does not. The other one has a limit point. Yeah, I pretty much just said it, but it's right there. I actually am going to pull up the textbook. Oops, that's my bookmarks. Too many analysis textbooks. Okay. Let's see. Alright, I have to study for this exam, so don't give me the answers on this. Like, antagonize me with meta hints. Connected. Which will have to be said to Pepe, probably. Where's the definition, though? That's the definition of separated. Connected. They have a limit point in common. There's still some space between them in the sense that no limit point is closed in one of these intervals. It's analysis. Said another way, the closure of 1, 2 is disjoint from 2, 5. And the closure of 2, 5 does not intersect 1, 2. Notice this is the same observation cannot be made. Okay, yeah. Two non-empty sets are separated if the closure of A intersect B and A intersect closure B are both empty. That's useful to know, I guess. A set E is disconnected if it can be written as E equals A union B, where A and B are non-empty separated sets. A set that is not disconnected is called a connected set. So I had a definition which is different from their definition, actually. But their definition probably makes more sense. My definition was like, if two sets, if an E equals a union of two sets, then one of those sets contains a convergent sequence and one contains the limit point. But they're different. Is this textbook based off your current class? I think usually it goes the other way around. Usually they base the class off the textbook because it's a lot harder to write a textbook. But yeah. It's a more topological definition. I kind of like this definition though. And we just have to show like an open interval is connected. separated if A intersect B and A intersect are both empty. Okay. Are non-empty separated sets. Was the question showing the intervals are connected or that all connected sets of that form? No, I think it's the first one. Prove the only connected subsets. Is proving that an arbitrary interval is connected. I'm still trying to wrap my head around this definition a little bit, though, because it's like defined in terms of, okay, so two sets are separated. I get that. A set is disconnected if if it can be written as a couple of separated sets. Wait, it seems like they're asking intervals are connected or that all connected sets of that form. Seems like they're asking the second thing, though. Wait, was the question showing that intervals are connected or that all connected sets of that form? I guess I'm not sure with the wording of your question. So, like, is it show that every connected set has to be one of these types? Show that the only connected subsets of R are... Oh shit, you might be right. Yeah, I might have, fuck. Yeah, I think you're right. Oh no. Oh no. No. Is it the idea that the intervals 1, 2, 2, 5 are both intervals that never reach the value 2 because it's not inclusive? They must be disconnected. Yes. It sounds like a diabolical question. Prove the only connected subsets of... Yeah, but I mean... Apology brain rot. Can you even say that? Can you even say that that's brain rot? That's like saying, like, astrophysics brain rot. What are the only connected subsets of R? Yeah, I mean, it's pretty easy to verify these through the definitions. That's like a much easier question. Like, You have to go through all possible forms of subsets of R, then work out which ones are connected. uh, no. Oh no. Our professor just proved it to us. Fuck. So you have to go through all possible subsets. So do you mean like the different permutations of the properties? Like you have to go through, okay, this one is open, this one's closed, this one's not open, not closed, this one's both, this one's like, is that what you're saying? Like split them into cases using those properties? Literally all the sunsets of R. No, even worse, literally all subsets. Singleton, finite sets, intervals, disjoint intervals. Uh, well, since R is connected, subsets can't be open and closed at the same time unless they're empty or the whole space. Wow, thanks. Yeah, that's like 2 less permutations. uh, Connected subset has at least 2 elements. It has to be an interval. Also, things like the Cantor set are included, and much worse. The Cantor set is included. Okay, yeah, I guess. So we just have to sort everything into cases. So I guess writing out like what those cases are is probably the best. Cantor sets are just disjoint intervals, though, which are never connected. The 2 element suggestion is great, yeah. That's what I was wondering. It's really Zen. Computed by taking arbitrary elements of our sets and then showing they meet the following properties. The upshot should be we can't really classify subsets of R. So proof can't rely on going through some crazy cases, so it should use some general properties of R. Are you saying you're, yeah, you started in the blunt yet? No, not yet. Are you saying that you're against this idea of literally every case ever? to go through all the possible forms of subsets of R. Then work out which ones are connected. Singleton finite sets, intervals, disjoint intervals. Depends on what cases you consider. If you know which case a set is disconnected, can you show R is not disconnected, hence it must be connected? You can start by proving that intervals are connected BTW. That can give you a good clue as to why the converse has to be true. The converse, you mean the converse of intervals? Like, what do you mean by the converse? You can start by proving the intervals are connected. Why would you start by proving the intervals are connected? The converse is the fact that connected subsets are almost always intervals. Besides singletons and the empty sets. The connected subsets are almost always intervals. I see. Why the converse has to be true? Okay. Well, is it going to be a bidirectional or something? You know, a set is disconnected. Show if you can. So if you can show some subset of the reals does not satisfy all cases of being disconnected, it must be connected. What's up, Big Pepe? Immediately start solving. Whoa. I gotta figure this out myself. I have an exam. Well, there's no way this question is on there, but... X is Clopin. X be a non-empty subset of R. We need... Wait, let X be a non-empty subset of R. We need R equals X if R is Clopin. Wait, that's what I was doing before, honestly. can't pronounce the first half of your name, but it ends with O3F. The first two cases, empty set and single point sets, are trivial, so the hard part is showing that every connected subset with more than one element is an interval. Oh. Give you a good clue because the order of the real numbers is deeply related to the fact that connected subsets are intervals. Order of the real numbers is deeply related to the fact that connected subsets are intervals. Alright. Well, so these first ones are just really, really obvious. You don't even, they're clearly both connected. Essentially, the hard part of this is the converse direction. Every connected subset of R is one of these three cases. Start by proving the intervals are connected. Okay. Open, closed, and infinite. Well, you don't have to divide them into open, closed, or finite. Only thing that matters is the interval property. That being just that they're ordered, you mean? They're ordered sets. Connected subsets are intervals. Means that if x, y are in I, there's an element between x and y that's also in I. So I wanted to show that if two numbers are contained in a connected subset, then every number between them must also be contained. And so you're saying it's the fact they're continuous in the above sense. Yeah. So we want to use the definition of a connected subset. Somehow that allows that property of being an interval. Well, if it's connected, then it can't be written as a union B. Can't be written as non-empty separated sets. What would that mean? If two numbers are contained in a connected subset, then every number between them must also be contained. That's honestly so sick. That made me a little bit more autistic for math. Because then if it has that property, then it's basically an interval. Call it AC so we can fit a B between them. What Pepe said helps. For the third, it suffices to show AB are in the connected set, then AB is a subset of S. That AB, like the interval AB, is a subset of S. Every element I'm confused about that. If A is a connected subset of R. Okay, maybe you meant okay. They're continuous in the left sense. Okay, hint. If there's a gap, can you partition S into two open sets? If there's a gap. Correct definition of an interval. S is connected and has two elements x, y. And there's an element z between x and y that is not in S. You can use that element to write S as a disjoint union of open sets. Which means that it's connected. Okay, okay, I get that, but you're writing the wrong definition. You assume instead that B is between A and C, and prove it has to be in S. And that B can be anything instead of just existing. Okay. Can you use this to create two sets that separate the set? Suppose by contradiction, I could find some number in between that is not in my connected set. Yeah, that's a good point, Johnny. Technically, open, closed, and finite. Then B, then A, B, C implies B and S is what the actual definition is. Okay, so then there's so if B is in S, then we're fine. But if B is not in S, then we've got two open intervals on either side of B. Which, if is true... Wait. Okay, so if... Yes, you're cooking. Don't look at chat. Okay. I'll turn off my brightness. Well, if it's not... If B isn't an S, can construct disjoint union, like something I don't know how to write that exactly, but you'd have like S1 up to B, B up to Sn. And we're just wanting to show this connected subset is an interval. And wait, so basically, like, with this definition, if B is... Whoa. If B is in S, then we just we have that S is an interval. And if B isn't an S, we have two open intervals. Well, they're not necessarily open, I guess. Because these could contain their intervals. But is that correct that if B is in S, oops. Slight mistake here, but you have the correct idea. What's the slight mistake? We can construct a disjoint union S equals which is, this is like, how do you construct S1 and Sn though? Yeah, you don't really, like, those are just random. If that holds for all A, C, and B, then yes, S is an interval. Yeah, how do you pick that? I'm not sure. That's just the notation I chose, and I guess it implies, like, counting where that's not possible. I mean, what if it's just, like, little s and, I don't know, like R? If you assume that S is bounded, but I don't think it has to be. I guess I'm confused by the fact that like, how else would you say splitting doesn't have to be with a bounded case. The proof might be a bit different. A equals elements of S less than B, and B's elements of S greater than B is the separation, yeah. Notice that A's closure can only contain things less than B or B itself, which is not in B. Similarly, B's closure does not interact with A, which is oh! Wait, and that's the definition of disconnected. And that means that if it's not an interval, it's disconnected. which proves that if it's an interval, it is connected. Oh my god. That's so sick. That's awesome. So, less than B. Well, I don't even think I like that notation really, because it deals with just like indexing. It's probably better to say S less than B. Well, S in S. Is that better? It's probably kind of hard to see this right now. That's so smart. The disjoint union. We don't even really need this last line. Like, if I think saying assuming towards a contradiction, like Johnny said, is probably is that all that's required? I thought there would be like hella more. That's why is that so elegant? You should also mention that any set which satisfies this property is actually an interval. Yeah, I guess you're right. I guess I shouldn't have removed that line. Where the fuck am I? I'm deep in the extra credit. So S is disconnected. Technically, you should also show that every interval is actually connected if it's not done in the book. Every interval is actually connected. Yeah, I guess you're right. So in terms of contradiction, B and S construct disjoint set. So S is disconnected. Well, actually the contradiction seems a little awkward to say here. If we're gonna next say that, but I don't know. If if BNS you don't have to be very terse. My teacher is kind of a... She said, well, she doesn't really answer emails, and that, I don't know, we were looking at last night, like, this one exam question that was just, like, completely wrong, and she also told us that, if you state the definition of convergence on a convergence problem, that's half the point, so I don't think you have to be that terse. And technically should show that every interval is actually connected. That's the other direction of the implication. Why would you have to show that? Every connected subset, if you have a connected subset of R, when doing these sorts of proofs, and there's lots of examples, contrapositive, counterexample, or contradiction. Induction is pretty cool. Whoever came up with induction is a genius. Are there other proof techniques than just like the basic ones they teach you in like intro to math? Or I don't want to get distracted, but isn't there a field about this? Treating proofs as mathematical objects. Yeah, we've covered in strong induction. That's so meta. That's awesome. Facilitating their analysis by mathematical techniques. When do you start analyzing those techniques you're analyzing the proofs by? Inductively defined data structures, list, boxed list, or trees, which are constructed according to the axioms and rules of inference of a given logical system. Proof theory is syntactic in nature, in contrast to model theory, which is semantic in nature. Look at proof trees. Method of analytic tableau. Semantic tableau, or plural tableau, also called an analytic tableau. Truth tree, or simply tree, is a decision procedure for centennial and related logics. What's centennial logic? Find reactive systems need different proofing systems. Logic and comp sci. I did kind of take logic and comp sci. I took like a theory of computation. Whoa. Combinatorics and graph theory is the best way to learn proofs when starting out. You don't think proof theory? How do you say this guy's last name? Is it Piano? Pino? Yeah, but you were saying you wanted to build intuition. A lot of times in tests, if you think you need to do like 20 cases, you should think, would someone really want to mark this? Yeah, I love like a metagaming test theory like that. Piano. 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 Okay. Piano. Bertrand Russell. Established by David Hilbert. Damn, that guy was cracked. So the idea of the program was that it could give finitery. Omega consistent theory, which is sufficiently strong to express certain simple arithmetic truths, cannot prove its own consistency. Undergrads with when recreational programming stream. Maybe this Sunday. Or, well, yeah, I'll do a recreational programming stream eventually. Definitely, like, this summer, like, I was thinking about, instead of doing an internship or something this summer, just, like, doing, like, just streaming, like, a project every day. Just trying to make, like, a kind of impressive project. Should probably be something, like, low level. Like, I've been thinking about making, like, an icicle simulator, you know, like, because there's tons of icicles where I live. And I was thinking, like what are the physics equations? There's like some heat transfer equations, but like what specifically makes an icicle form, and also can you maximize the size of an icicle? And if so, like then that could be used for like cutting edge research in like festive northern towns, you know, because they could like once I have my simulation with like the temperatures and stuff, and the like we know the optimal conditions to make an icicle, you could sell like a little device you put on your window that like leaks heat at like just the right amount to like to absolutely create the biggest icicle ever. Making a math standard for I love how all the non-programming people are like or you could do math or you could learn math. You better not do anything applied. You should learn something really abstract. The author of the Lean papers making an AI company now. He's pairing LLMs with Lean. Yeah, I would actually like to use Lean. Pairing LLMs with Lean. Yeah, that's That's possibly a recipe for the end of human mathematicians if just LLMs are churning lean out. But, wait, self-verifying theories? Much weaker than self-verifying theories. How does that even work? Graph theory? I uninstalled math right when I started struggling with linear algebra 2 proofs. Yeah. True. That's the thing, like, math is really cool, but I'm more likely going to be a programmer than a mathematician. Although, like, I'll do stuff that involves both for sure. But I was thinking, like, if I'm not working at a company interning and I'm trying to actually make a good project myself, it would probably involve, like, getting other people on board too, or at least, like, consulting with other people. So, like, I don't have to be insanely good at math as long as I can get someone who is really good at math to do the math part. What is pretty weak? That just sounds like semantic. Oh, you know, they're not they're not that good. It doesn't sound like a math term. It's like saying somewhat. So you should take advantage of this by doing something different. What do you mean something different? Like learning category theory? I guess that's true. Yeah. Okay, category theory it is. Yeah, I guess. I got manipulated into it, actually. I didn't really think of it myself. Yeah. Okay. Do I smell an algebraist? Worst mistake of my life, kinda. How hard is it to learn category theory? Damn mathematicians. Hold on, I gotta. My mom is here to drop off some random stuff for me, so I have to go for it 1 sec. But I'll be back in like I don't know 5-10 minutes. Alright, hopefully that killed all interest in the stream. That would be good. Then maybe Johnny won't be here. Oh, damn it. Alright, what did I miss? Math lab, it's a great idea. What do y'all do? Study/work as. People keep saying functional programming is like category theory. Oh, US4 Tnyanyan. I never know how to say your name. You Sat Nyan. What's up? Damn it, I zoomed my chat window in too close. How do I zoom this out? There we go. Now I can't scroll. What the fuck? You'll need the flimsiest bit of category 3 to learn what a monad is. Isn't a monad just like a meta type that wraps around another type and adds some metadata to it or something? Okay. So the question is, did we finish problem 4? It's hard to say. Johnny said before that we should also prove that an interval is connected. And someone else who is smart said, the category of endofunctors. But a monad is a monoid object in the category of endofunctors and some other A monad is a monoid in the category of endofunctors. What does that even mean? That's nonsense. That's what? Wait. If you were to prove that an interval is connected, find out this summer what it means. What kind of prereqs does it have in terms of understanding? Anyway, looking at this problem again, if you wanted to show that an interval was connected, isn't it just the same argument? Like, pick a point and then split it into two, and then you have, like, that the interval is the disjoint union of two pick a point, split it into two, I've done algebra classes, just like not super comprehensively as much as I would like to. Like abstract and linear. Is that even worth doing the argument for? It's just the same thing but backwards, basically. I'm gonna skip it for now, for interest of, I don't know, being interesting. There we go. What's covered in a U.S. abstract algebra course? Groups, rings, fields. Yeah, I don't think we got, like, I had not have a good professor for that class, and I think my university for math is pretty bad. Like, Big Pepe, I think, has a better math education just self-studying in Pakistan than I have it at this university. Like, covered groups pretty comprehensively, but the other two, typically after learning group, rings, and vector spaces, what the fuck? It's like a typhoon outside my house right now. Some, like, person's window just blew off. Show that the following functions are continuous in their domain. I haven't encountered, actually, a continuity problem yet. Dirichlet. How do you say that word? Dirichlet? Dirichlet? Although it's common practice in calculus courses to discuss continuity before differentiation, historically mathematicians' attention to the concept of continuity came long after the derivative was in wide use. Fermat was using tangent lines to solve optimization problems as early as 1629. That's interesting. On the other hand, it was not until around 1820 that Cauchy, Bolzano, and Weierstrass and others began to characterize continuity in terms more rigorous than prevailing intuitive notions such as unbroken curves or functions that don't have no jumps or gaps. That's what I think continuity is. What's wrong with that? The basic reason for this 200-year waiting period lies in the fact that for most of the time, the very notion of function did not really permit discontinuities. Functions were entities such as polynomials, sines, and cosines, always smooth and continuous over the relevant domains. The gradual liberation of the term function to its modern understanding, a rule associating unique output with a given input, was simultaneous with 19th century investigations into the behavior of infinite series. Was immediately tied to the ability to represent a function as a limit of polynomials. Called a power series, or as a limit of sums of sines and cosines, called a trigonometric or Fourier series. Typical question for Cauchy and his contemporaries was whether the continuity of the limiting polynomials or trigonometric functions necessarily implied the limit f would also be continuous. Sequences and series of functions are the topic of Chapter 6. What is relevant is finding a rigorous definition of continuity. Any significant progress on the question of whether or not the limit of continuous functions is continuous, or Cauchy for us, necessarily depends on a definition of continuity that does not rely on no holes or no gaps. What a mathematically unambiguous definition for the limit of a sequence in hand, we are well on our way towards a rigorous understanding of continuity. So we define continuity as a point C in A to mean that if x in A is chosen near C, then f of x will be near C. Dirichlet. The problem with that is functions could be continuous at a single point and nowhere else. Like the inverse of the absolute value, you mean? The relative value? Oh my god. We have a definition for the limit of a sequence. It's not entirely clear what's meant by the limit of a function. The subtleties that arise as we try to fashion such a definition are well illustrated via a family of examples, all based on the idea of the prominent German mathematician Peter Lejeune Dirichlet. Dirichlet's idea was to define a function g in a piecewise manner, based on whether or not the input variable x is rational or irrational. I mean, something more effed up. Yeah, take a function defined at a single point. Yeah, that would work. Okay. Specifically, let g of x equal 1 if x is rational and 0 if x is irrational. Okay, that's funky. we indicate that's a weird looking function. We indicate the intricate way that Q and I fit inside R. What's I? Integers? Fit inside R makes an accurate graph of G technically impossible to draw. But 4.1 illustrates the basic idea. It stands for irrationals. Oh. Yeah. Yeah, that makes sense. Does it make sense to attach a value to the expression limit as x goes to 1/2 of g of x? One idea is to consider a sequence x of n approaching 1/2. Or consider a sequence going to 1/2. Using our notion of the limit of a sequence, we might try to define limit as x goes to 1/2 is simply the limit of the sequence g x of n, but notice that this limit depends on how the sequence is chosen. If each xn is irrational, then g xn equals 1. On the other hand, if xn is irrational, then for each n, yeah. Does it make sense to attach a value to the expression? Most additive functions on R. Modified Dirichlet function. H of x. Where is 4.1? Oh, right. Dirichlet's function. Yeah, it's just 2 lines of dots. The unacceptable situation demands that we work harder on our definition of functional limits. We want the value of limit as x goes to c g of x to be dependent of how we approach c. In this particular case, the definition of a functional limit that we agreed on should lead to the conclusion that the limit doesn't exist. Postponing the search for formal definitions for the moment, we should nonetheless realize that Dirichlet's function is not continuous at c equals 1/2. In fact, the real significance of this function is that there is nothing unique about the point c equals 1/2 because both the irrational and rationals. Why did they say the set of irrationals here the second time, but like not the first time? Are dense in the real line. It follows that for any integer, or for any z, I guess that's not an integer, in R, we can find a sequence xn in rationals and yn in irrationals such that the limit of the sequences both converge to z. Or dense in the real line. What does it mean for something to be dense? Other than stupid. In the jargon of analysis, Dirichlet's function is nowhere continuous function on R. That's sick. What happens if we adjust the definition of g of x in the following way? So now it goes up. We take c different from 0, and just as before, we can construct sequences x of n to c of rationals and y of n to c of irrationals, such that the limit of xn and yn okay, I buy that. You can also choose a sequence of irrationals. That's what it means for both subsets to be dense. One definition: a set is dense in R if it intersects every non-open subset of R. The closure of a dense set is the whole set of R. Okay. Cool. Dense. Is there like an alternative definition of like sparse? Closure of a dense set is the whole R. The same line of reasoning reveals that g of x is not continuous. Okay, yeah. And just as before, we can construct sequences of rationals and irrationals. Approaching C so that limit equals C and that equals 0. Thus H is not continuous at every point because we have two sequences approaching different values. It's typically called meager. Sparse means the complement is dense. Why are there so many damn terms in this math? Doesn't meager mean measure 0? So meager is purely topological, not measure theoretic. Is measure theory like how big sets are? And topology is just how what properties they have without really caring about size. However, these two limits are both equal to 0. In fact, it appears as though no matter how we construct a sequence converging to 0, it will always be the case that Zn equals 0 and a limit, then these two limits are both equal to 0. Oh, if c equals 0, however, then these two limits will be equal to 0. In fact, it appears as though no matter how we construct a sequence converging to 0, it'll always be the case that the limit of Zn equals 0. This observation goes to the heart of what we want functional limits to entail. To assert that as x approaches c of x equals limit would imply that for all sequences will go to the same constant. For reasons not yet apparent, it's beneficial to fashion the definition for functional limits in terms of neighborhoods constructed around C and L. We'll quickly see, however, that this topological formulation is equivalent to the sequential characterization we have arrived at here. Is a nowhere dense subset. Measure theory is one of the ways to generalize real analysis. You can integrate weird functions that you can't do with normal integrals. It's also the foundation of probability theory, really. One of the ways to generalize real analysis. Everything can always be generalized more for some freaky reason. We will quickly see, however, that this topological formulation is equivalent to the sequential characterization we have arrived at here. To this point, we have been discussing continuity of a function at a particular point. This is a significant departure from thinking of continuous functions as curves that can be drawn without lifting the pen from the paper. It leads to some fascinating questions by K.J. Tomei, discussing the function 1, if x equals 0, 1 over n if m over n is in the rationals minus 0 is in lowest terms with n greater than 0, and 0 if x is not in the rationals. If c is in the rationals, then t of c greater than 0. Because the set of irrationals is dense in R, we can find a sequence y at n converging to c. The result is that the limit of yn equals 0 does not equal t of c. Yeah. What? Fails to be continuous at any rational point. The twist comes when we try this argument with some irrational point in the domain, such as root 2. All irrational values get mapped to 0, so the natural thing would be to consider a sequence of rational numbers that converges to root 2. Now root 2 is 141,213. So a good start on a particular sequence of rational approximations. What the fuck? 14142. And they just... Are you allowed to do that? But notice the denominators of the fractions are getting larger. In this case, the sequence t of xn begins multiplying by 20. And this is fast approaching t of root 2. See, this always happens. The closer a rational number is chosen to a fixed irrational number, then the larger its denominator must necessarily be. That's why you can approximate any real number by rational numbers. Therefore, the rationals are dense. That is cool. Is there an example of a function with the opposite property? In other words, does there exist a function defined on all of R that is continuous on Q but fails to be continuous on the irrationals? Could the set of discontinuities of a particular function be arbitrary? If we are given some a subset R, is it always possible to find a function that's continuous only on the set A complement? In each of the examples in this section, the functions are defined to have erratic oscillations or endpoints in the domain. What conclusions can we be drawn if we restrict our attention to functions that are somewhat less volatile? One such class of functions is called the monotone functions, which are either increasing or decreasing on a given domain. What might we be able to say about the set of discontinuities of a monotone function on R? Functional... Are we going to get to continuity ever? Consider a function... Okay, but now we're getting to some more definitional stuff. Function from A to R. Recall that the limit point C of A is a point with the property that every epsilon neighborhood of C intersects A at some point other than C. Yeah. Equivalently, C is a limit point of A if and only if C equals lim xn for some sequence xn subset A, where xn does not equal C. It's not just a constant series of C. It is important to remember that limit points of A do not necessarily belong to the set A unless A is closed. Right. If C is a limit point of the domain of F, then intuitively the statement x approaches C is intended to convey that values of f of x get arbitrarily close to L as x is chosen closer and closer to C. The issue of what happens is when x equals C is irrelevant from the point of view of functional limits. In fact, C need not even be in the domain of F. Monotone functions are differentiable almost everywhere. When are they not? Structure of the definition of functional limits allows the challenge response pattern established in the definition for the limit of a sequence. For example, sine x over x. I'm assuming you mean sine x over x, not sine x over x. Approaches 1 when x approaches 0, despite the fact that sine 0 over 0 is not defined. Sine x approaches, yeah. No, this is Zathura. This is very much Zathura. See? Well, how do I prove it? It just has the headlights. It's Zathura, I swear. But almost everywhere it means if they only fail to be differentiable at a set of measure 0. Very small sets in some sense. What does of measure 0 mean? What does very small mean? Like 3 items? 4 items? What does that mean? Also, what do you guys think about probability and statistics? You can think of it as sort of probability. Fake math. Probability is awesome. I think it's boring. The two extremes. No, probability isn't it pretty useful? Probability is goated. Oh, wait. But statistics... Probability is... is goated. So is statistics, but statistics sucks balls. It's goated and it sucks balls, I guess. I was thinking about this the other day because I watched this Jonathan Blow talk about civilization. Like sometimes technology will kind of erode over time because like you have to pass down complex tribal knowledge to the next generation of people, and there's a little bit lost. That must be like a huge problem in math. Like what if some guy is like brilliant and like knows all this stuff, but then like he dies before like anyone else can fully like ask him questions about certain things, and then he leaves like a bunch of, especially now where like math has gotten like it's exploded and all the fields are so like specialists can not understand each other's work. like it must be kind of hard to transfer your knowledge of something, and there must be like a lot of duplication of work and stuff, but I don't know. Probabilistic methods make those proofs. That's what happened with Riemann, Galois, Ramanujan, etc. I think LOL is kind of overused. I do that too, but like, is that funny at all that those guys like died and we lost like so much math? No, that's a horrible tragedy. That's why we need to prove things carefully and why you actually need to learn real analysis properly instead of being okay with continuous means I can draw it without lifting my pen. Fair enough, I'll get back to work. If C is a limit point of the domain of F, then intuitively statement is intended to convey. Okay, I read that. Structure the definition of functional limits follows the challenge response pattern established by the sequence. Okay, called it a given sequence and the limit of. Ow! Stuck my finger in my eye. The assertion. The assertion limit an equals L implies that for every. Oh, this is nice. This is, yeah, I like this. For every epsilon neighborhood centered at L, there's a point in the sequence, call it AN, after which all the terms of AN fall in AL. Each epsilon neighborhood represents a particular challenge, and each N is their representative response. For the functional limit statements, such as the challenges are made in the form of an arbitrary epsilon neighborhood around L, but the response this time is a delta neighborhood centered at C. So is it like the radius of the delta neighborhood? Okay, finally, 4.2.1. For Matt's last theorem. That would be like the biggest, absolutely the biggest troll you could pull off if you were a mathematician and like you knew you were about to die. If you were like really talented, I guess you'd have to be kind of a genius, but to make this actually work. But then you're like, oh, and I proved this and this and this and this. I have proofs of all these really hard things, but you don't, and then just people end up haunting them forever. Okay. F from A to R, let C be a limit point of the domain of A. We say that limit x goes to C, f of x equals L, provided that epsilon greater than 0, there exists a delta greater than 0, that whenever x minus c is contained between 0 and delta, and x in A, it follows that f of x minus L is contained in epsilon. epsilon delta version, and this definition for functional limits, recall it, the statement is equivalent to epsilon ball. Likewise, the statement is equivalent to delta ball. And then that restriction is just saying x can't equal c. Okay. Just economical in what sense? Like, you're not wasting ink? Isn't there some weird mathematical notation that only exists because of, like, ink? It's something to do with trig functions. Or it's like, yeah, it's like the inverse of a function, like printing a -1. What is it? The inverse, yeah, the inverse of something is done in a certain way that's like not what it should be. I think it's of trig functions, just because they wanted to save ink. That's a little more than a change in notation, but it does help to emphasize the geometric nature of what's happening. Functional limit topological version. What was the other version? Oh, just the nothing version. C be a limit point of the domain F from A to R. We say that limit as x goes to C equals L, provided that for every epsilon neighborhood, functional limit, functorial. Parenthetical reminder. Wait, this this isn't continuity. This is limits. I need more tissues. God damn it. Okay, parenthetical reminder. X and A, present in both versions of the definition, is included to ensure that X is an allowable input for the function in question. When no confusion is likely, we can omit this reminder with the understanding that the appearance of f of x carries with it the implicit assumption that x is in the domain of f. Okay. On a related note, there is no reason to discuss functional limits at isolated points of the domain. Thus, functional limits will only be considered as x tends towards a limit point of the function's domain. Isolated just as it doesn't converge. What? That's all well and good, and I understand what they're going for there, but what about continuity? What's up, Linkarzu? I feel like, honestly, everyone should go to the psych ward. Unironically, like, the people in the psych ward were more productive than anyone else I've ever met. Finally, continuity. The modern world is just so damn distracting. How's your YouTube addiction, Linkarzu? We now come to a significant milestone in our progress towards a rigorous theory of real valued functions. Finally, a proper definition for the seminal concept of continuity that avoids intuitive appeals to unbroken curves or functions without jumps or holes. Definition 4.3.1 is continuous at a point C in A if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus c is less than delta and x in A, okay. Yeah. We don't need that, though. The parenthetical, like they said, it follows that f of x minus f of c is less than epsilon. That's it? If A is continuous at every point in the domain A, then we say that f is continuous on A. For all epsilon greater than I don't know. I have I haven't taken I haven't taken meth for a couple of hours, so I'm feeling pretty good. I mean, no, it's not that underwhelming. It's pretty cool, I guess. It's just like it's really similar to continuity. Yeah, it's really similar. They say that right below, too. I feel like YouTube addiction is harder to break than meth. Because meth, like, at least when you stop doing meth, like, I don't know, you don't feel that bad. You just feel like, you feel like kind of tired and stuff, but, like, if you stop doing YouTube, then you have to, like, face the realities of life. And that's, like, unbearable. I would say YouTube is more addictive than meth. Definition of continuity looks much like the definition of functional limits, a few subtle differences. The most important is that we require the point C to be in the domain of F. The value of f of c then becomes the value of the limit as x approaches c of f of x. With this observation in mind, it is tempting to shorten the definition 4.3.1 to say that f is continuous. at C is an element of A. It's so beautiful, I'm crying. Okay, let's see if this is... Maybe they'll have an example. The obsidian guy? What do you mean, what happened to him? He's still alive? Did you watch that whole video? Damn, you really do have a YouTube addiction. It's tempting to shorten the definition to say that f is continuous and c is a if. It is tempting to do that. I was going to do that. This is fine as long as c is a limit point of a. If c is an isolated point of a, then the limit f of c, limit of that thing, I can't talk right now, isn't defined by definition 4.3.1, can still be applied. An unremarkable but noteworthy consequence of this definition is that functions are continuous at isolated points of their domains. Is that unremarkable? That seems kind of unintuitive. This is fine as long as c is a limit point of a. If c is an isolated point of a, then the limit of x goes to c isn't defined. Oh. Characterizations of... Alright, have fun watching YouTube, bro. Let A... Unremarkable will make you remark. Yeah, for real. Okay, characterizations of continuity. The function is continuous if and only if any one of the following three conditions is met. Any one of. Oh, I thought they meant exactly one of for a second. That would have been a logical fallacy, I guess. For all epsilon, there exists a delta such that that implies that. For all epsilon balls are round f of x, or f of c, there exists a delta ball around c with the property that x is in the delta ball and x in A implies f of x in, okay, for all xn going to C with xn and A, it follows that f of xn goes to f of C. And if it's a limit point, it's equivalent to the limit equaling C. Statement 1 is just the definition. Statement 2 is the standard rewording, using topological neighborhoods in place of absolute value. Okay. And yeah, all right, I think I got it. I'm gonna try to prove those suckers. Oh. Okay. Show that the following functions are continuous in their domain. So, an arbitrary point for continuous in their domain, we have to show. For some reason, that Let's Solve Some Exercises just has like such a I don't know, like children's TV show energy. All right, let's go solve some exercises. But it's funny because it's analysis. It's not a kids show. All right, let's do it. Okay, so we have to do this for C in A. I'm glad that's the tone you meant. So for all epsilon, there exists a delta such that x minus c okay. Okay. Now what? Now f of x equals 1 over x. And we have to show that there exists we want to show that there exists a delta, and that delta is probably going to be defined in terms of the epsilon. Or yeah, how is that going to go down? There exists a delta such that that's always true. You're getting the of this stuff. Fried in ESP32. You were so eager to say that you couldn't include the only verb that made it make sense. Okay, and let the function f is continuous at C if and only if. Yeah, okay. And we can assume that that's true and try to get it to imply that f of x minus f of c is less than epsilon. Okay. Oh. Oh, this is kind of cool, actually, because showing that x minus c is less than delta. Oh, this... I was zoning out for a second. But this is really cool because if you have delta defined in terms of epsilon, then you have to like kind of apply those functions and try to get... So we have to kind of work backwards from what we want, I guess. Which would be like 1 over x minus whatever c is less than epsilon. Okay, so how is this gonna work? We need this to define the delta. Is the algebra here going to involve like triangle inequality? Or reverse triangle inequality? Or are we going to have to like combine these in a fancy way? Please tell me it's not required. You indeed want to start with this and rewrite it so you get something with delta. Depends on the girl. Oh, this proof for getting a GF. I didn't see. Oh. It depends on the girl. You want to get something with x minus c instead of the reciprocals? Yeah, and I was just thinking, like, well, am I just, like, super slow at algebra? It seems kind of... Well, wait. What if you, like, combine them? What if you go, like, multiply by c over c, cx, multiplied by x over x, so you'd get c minus x over cx. And then you go, like, you hit it with a flipperino, and then you go like that, and then this becomes a reciprocal, and then this becomes a c minus x, and this becomes a cx, and then you say, no, well, wait, maybe. Like, I'm just confused on flipping this fraction. Like, would this simplify out to x minus c? Quantitativity's limits. I think that's kind of off limits. We're a couple levels underneath that. Keep x minus c on one side and move the other stuff to the other. X minus c will be bounded by delta. Keep x minus c on one side and move the other stuff to the other. There's literally no music in the background. X minus c will be bounded by delta. Keep x minus c on one side and move the stuff to the other. Keep x minus c on one side. Wait, so maybe I messed up at this step then. And it should be like this is greater than epsilon times cx. Yeah, why not? I could, we want delta less than epsilon cx. Then we'd be done, but delta can't depend on x. Yeah. That's true. That's true. So try removing x dependence by assuming x is very close to c, then use inequalities to approximate x by c. Try to not give direct hints. Good on you, Big Pepe. Try removing x dependence by assuming x is very close to c. What the fuck? Did you see those balloons go up? What was that? So it might sound like bullshit. C is very close to x. If C is very close to x, then we're going to be very close to c squared there on that side. But that's weird because That might break the inequality, I don't know. Remember that we can make x minus c as small as we like. Just assume x minus c is less than c halves. And use that to proceed. If x minus c is less than c halves, that is not crazy. I'm not getting the intuition for that crazy, but so if this is less than c halves, I mean, then clearly it's less than yeah. If you're adding on an extra x and an epsilon, well, the epsilon might be less than 1. Alright, good luck, Poseidon. Okay. Absolute value x, absolute value c, don't forget it's absolute value x. Yeah, you're right. If this is less than c halves, it's certainly less than c squared halves, which is c squared, but x is greater than c halves. Oh, x is greater than c halves. Yeah, that's obviously implied. Yeah. X is. Yeah. Uh, so epsilon c x is greater than epsilon c squared over 2. So it suffices to choose delta at most both c halves and epsilon c2. Yeah, I get it now, I guess. Well, apartment tour was good. Thanks for being parasocial. Wait, can you explain real quick? Why we can't have this in terms of x, but we can have it in terms of c. Specifically delta min c over 2 and epsilon c over 2 squared. C is a fixed number. X is a variable. See that x is chosen after the delta, but the delta after the c. Order of quantifiers. You want x to be within delta of c. Yeah. Circular definition. Yeah, how far away is it? It's x far away. Yeah. That makes sense. It's as far away as it is far away. What's also interesting is every point of. Well, no, this doesn't work. This definition, like limit x approaching c of f of x equals f of c would work for an open set or a closed set if it contains all its limit points. But since this interval is not open or closed, can't use that. You can use this definition just fine. But it contains no isolated points, I guess. All the elements of the interval are still limit points of the interval. Oh, yeah. Wait 1 sec. I gotta fix something. Okay, all cool. So that's the scratch work. If we say, let epsilon be arbitrary, let delta equals the min of C halves and epsilon C squared over 2 I guess it would be nicer if these were in parentheses a little bit. And then x minus c less than c2 alone. That will serve as one bound. Then go back and work on the don't forget, because constant, the denominator that you write as c times absolute value x, and you can always terms to the numerator of the other side of the inequality. Leave c minus x less than c halves alone, that will serve as one bound. Then go back and work on the 1 over x minus 1 over c. Don't forget, because constant, the denominator you can write as, you will always, terms of the numerator to the other side of the inequality. Not exactly sure what you're saying, but wait, so getting rid of that scratch work, if we're letting delta be the minimum of those two, if delta equals c halves, then we have delta is less than, well, is greater than x minus c. No. Let x at 0, x minus c less than delta, and x in domain of f. Let x such that 0 oh yeah, you need the 0. Let x Okay. Oh, good call, Johnny. Now x minus c less than delta implies x minus c less than c over 2 which implies x minus c, well, xc over x minus c is less than c. Well, no, I'm getting confused here a lot by this argument of I'm getting confused by this argument of the minimum of c over 2 and epsilon squared c over, or epsilon c squared over 2. Why is that necessary to have that minimum in there? Because the algebra, like, done backwards makes a lot of sense for me for c squared epsilon. Because then we get that implication pretty easily. And this one x minus c is less than xc epsilon. Works backward with your scratch. Okay. It's less than epsilon. Like that I get, but the minimum makes it funky. But I'll look into that in a sec after this. So, which then we get what we need, which is 1 over x minus 1 over c less than epsilon, which is done. But yeah, why is that minimum there? I don't get that in the slightest. Point of choosing the minimum that x minus c is less than delta implies that x minus c is less than c over 2. Just think about the minimum as an and. Oh, and the reason we do that minimum is because gotcha. It's less than the minimum. It's less than both terms. The point of choosing the minimum implies x minus c is less than c halves, and x minus c is less than epsilon squared over 2 at the same time. As and. The minimum is and. Okay, the minimum is and makes a lot more sense. Like I'm trying to think though. The minimum as and because that seems more like an or. As someone who didn't pay attention earlier, it's not clear right now how you get from epsilon c squared over 2 to epsilon xc. X minus c is less than c halves. So absolute value x is greater than c halves. And x minus c over epsilon wait, and x minus c, I think, did you mean less than? If you're subtracting something from c and are left with c halves, and are left with less than c halves, x itself has to be greater than c halves. But x minus c also has to obey the other inequality you discovered of epsilon times c squared over 2. In this case, it's an and, but it's less than the minimum. I'm confused though, because wouldn't that be it's less than the maximum implies and? Because saying less than the minimum seems like it could be less than one of them, but not the other one. If you're subtracting something from x and left with c halves, then x itself has to be greater than c halves. X minus c is smaller than the smaller of c halves. And epsilon c squared halves, so it must be smaller than both. Oh, duh, yeah. Yeah. Yeah, I get it. Yeah, okay. Yeah. Right. It's less than. I see. Yeah. Yeah. Min means and. Greater than max, less than min means and. So do I still have to clarify more in this backwards work, like how that substitution is happening? Like this right here is maybe not entirely clear. So I could say like since x well, you're subtracting something from x and are left with c halves. X itself has to be greater than c halves. No, I'm doing it for Johnny. Alrighty, cool. X needs to be closer to C. We consider two cases of delta where one solves for one over x and the other x minus C. Someone has to hire Big Pepe. That's clever. Alright, last problem on the homework. And then I'm probably going to break for lunch. And then come back and, well, there's... This is solved. This is arguably solved. This is the whole thing where you have to prove that, yeah. What's going on out there? Okay. What are we doing? Continuity of negative m to r for f of x equals x to the n. Is there any link in the description I can access? Have you thought about checking? Wouldn't it be easier to check yourself than asking? Okay. Let epsilon greater than 0 be arbitrary. Okay. The basic rule yet here? What basic rule? And assume that, well, and you can generalize here, that might be easier. Look at definition. Product of limits is the limit of the product. And then just do that for all x. Induction on n also works. What do you mean generalizing? for n equals 2, 3, 4, 5. Talking about is the product of limits. Product of limits is the limit of a product of functions. Why is that helpful here? Because this is just x times itself a bunch of times. And you do you can induct your way up to the general case. Okay, yeah, I guess let's do it. So base case n equals 1. More directly with the binomial theorem. How'd you do it with the binomial theorem? Just like say that if x, like split x into two things and then get factors, and then get the binomial expansion and then use like Bernoulli's inequality. Confusing. Okay. So that's just trying to get n equals 1, epsilon greater than 0, c and mm, delta just equals 1 over epsilon. Which implies, oh, no. Let x greater than 0 less than, is x greater than 0 here though? Because we go from a negative value. Or you could also do the general case directly. Yeah. Then why are we inducting? I would rather not induct. Then you could use the triangle inequality. Bound the sum using the fact that both x and c lie in negative mm. Which we can factor. Why is boundedness of the sum important? Oh, so we can derive. Oh, because we're working backwards to find. Yeah. General case is just more annoying algebra, but on the other hand, for the simpler induction method, you could use the product rule. I'm not sure. You can. Product of two continuous functions is continuous. I think that would be allowed. But maybe not. Did World War III just start? Alright, I'm going to try to do the general case. Not looking at chat. Now we want to work backwards to get that x to the n minus c to the n is less than delta. Or less than epsilon. No, less than delta, yeah. And we want x minus c. So could this be factored? Could it be factored? We need some middle term to add and subtract. Using the binomial theorem. The fact that your domain is bounded will make the binomial way easier, and it makes me think that's the way I need to do it. And the delta is dependent on the epsilon. Why is the domain being bounded make this easier? Oh yeah, there was someone in Dubai getting bombed earlier, yeah. X to the n, c to the n, less than nm. Oh. Less than nm to the n minus 1. Okay. X, this is less than nm n minus 1 of x minus c. And then you could just move that around. And then get your epsilon like that. You'll see why it helps once you factor expression using the triangle inequality. Why? Yeah, I don't get that factorization. And why is m in there? You see, once you factor your expression using the triangle inequality, use x to the n c to the n equals x minus c. times x to the n minus 1 right, yeah, x to the n, c x to the n, c to the n minus 1. Yeah, I recognize that. First factor. Okay, so alright, so we get an x minus c in here, and then we get the binomial theorem in here. X to the n plus cx n minus 1 plus dot 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 plus c to the n minus 1. And then we have a big ass thing. And now you can get some large sum to which you should apply the triangle inequality. Now you can use that everything lies in the interval negative mn. Get some large sum to which you should apply the triangle inequality. So each one of those terms times your terms on the factored expression should only go up to an exponent of n minus 1. Oh, right. Yeah. Yeah. Even here. Okay. How is the triangle inequality going to come into play here, though? If each of these terms this is all less than so this is less than like all all these terms, so we could get rid of terms that we don't really need. Why is this fact that this is bounded useful? Now you can see that everything lies in the interval. Negative m to m. Why does everything lie in the interval negative m to m? I mean, if C is in there. Well, first we should split the absolute values so we get absolute value Thanks, I appreciate that. I am Rost. I like to think I'm a pretty huggable guy. I feel like I'm going to be a very huggable father one day. But splitting this... to sum gives x, and apply the triangle inequality to sum gives x to the n minus 1 plus c gives absolute value x to the n minus 1, absolute value c, absolute value x to the n minus 2, yeah, okay. But I'm still not really getting, like, yeah, you could throw absolute values in all of these. AF. Using the bound that's x to the n minus c to the n is less than or equal to x minus c times n times m. And m n minus 1. And m is just a general term of the... You want to find a range for x around c, so that c plus delta, or c minus delta, c plus delta, that inequality is true. a range for x around C. So C plus delta, C minus delta, where the inequality is true. If you can separate the x minus C, you can find a loose inequality of the sum. We know that x and C are less than m. So each term is less than m to the n. So the sum is less than n m to the n. Now divide both sides by n m n. You can guess delta for which the inequality is true. Since both x and c lie in the interval, we have both less than negative m, less than m. They're between m and m. You want to find a range for x around C. C minus delta, C plus delta, where the inequality is true. If you can separate x minus C, you can find a loose inequality of the sum. So m is a fixed positive real number defining the interval. Oh! Oh, the proof works for any m greater than 0. If m equals 0, it's just set 0. Continuity is trivial. For m greater than 0, we can use x, absolute value x less than m, and absolute value c to bound the sum. Oh. Oh. So every one of those terms is less than m. And that's why you're able to n times m to the n minus 1. N times n. I guess so. So are we just throwing out like a lot of the terms of the sum in order to keep that inequality working? I mean, it would work regardless, but in order to c times x to the n minus 2. Oh, yeah, sure. X. But so Like, I guess I'm just slightly confused on how we're getting to m. Like mn to the n minus 1. So that x and the c are both bounded by m, but where's the extra n coming in there? No, n times m to the n minus 1. Oops. By saying it's n, by saying it's less than or equal to n times m, we get a simple guarantee no matter what x and c are, as long as they're between negative m and m, that sum is never bigger than n. Wait, does the n there come from, and by the n there, I'm talking about that n. Does that come from the number of terms in the distribution? Oh, it does. Yeah. Oh, okay. Oh. Then since equals x minus c times that sum, we get the clean inequality x minus c is less than n times m. Okay. And then, so we get WTF. Something's funky with this. And it comes from the number of terms in the expanded sum. Okay, thank you. That makes sense. Oh, and because both x and c we have bounded by m, then the exponent property will just apply, and they're both going to always add up to n minus 1. Damn, that's clever. Triangle inequality is adding a bunch of things up is less than or equal to. You are using this between 2 and 3. Right, just to get this sum out of those. We're not using it like infinitely. Okay, well, so this is less than epsilon, but this x minus c times x n minus 1 oh, no. What the fuck am I doing? That's so cool. That's awesome. Gotta love math. How am I gonna do this? I want to get rid of those last dollar signs. And that one. And like that. And like that. How does that look? Okay, well this is so then we get that is less than or equal to, well, is less than epsilon over x minus or we get x minus c is less than epsilon over n times m to the n minus 1. Where do you even get these questions? These are so good from my class. You want to find the delta for which the inequality is true. But the delta is going to be in terms of the epsilon. Can't we say that so let delta equals is that order in the converse too? Yeah, I mean the delta is epsilon over that bad boy. Now let x, okay, so in the previous one we said let x greater than 0, less than that, but now our bounds are different. So would it be let x, like let negative m less than x less than m? You get that for x in c plus delta, f of xc is less than epsilon. What's the bound on this? Oh, I guess it's still 0. What am I saying? Okay, now x minus c less than less than this implies, probably want new lines, x minus c actually, do we? X minus c is less than times n minus 1 less than epsilon implies x minus c times x n minus 1 plus x n minus 2 plus dot 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 plus c n minus 1 less than epsilon implies x to the n minus x to the c is less than epsilon. Scratch work is no longer necessary. You also want x in, but this will be necessary in our bound. Oh, this will be necessary in our bound. Yeah, good call. And x just think of it as saying x in range of c minus delta to c plus delta. That's what x minus c delta means, but you're visualizing it, otherwise you're just parsing formulas and it's not intuitive. Yeah, I think I have to let that. yeah, I guess I did skip a couple of steps here. To see why you chose delta that way? Well, we have this here. Is there something there that's missing that you want to see? Explicitly bound the sum n 135, 136. Explicitly bound the sum to less than using the triangle inequality. Without that bound, you can't jump. Do you mean just saying like oh my god, since x c is less than m squared, well, x and c, like just text like that? Without that bound, you can't jump. Well, the triangle inequality, like I understand the individual components of the triangle inequality and whatnot, but using the triangle inequality, the sum is less than n times n. since and oh, I think it might be better to say since that sum is less than or equal to times n m n minus 1. You need to explicitly use the bound x is less than m, sum is less than m, n via triangle inequality plus triangle inequality plus x c. Yo, thanks for the $2. Glad you enjoy the videos. Final line should be is less than epsilon. Not wait, I'm what? Oh, you're right about that. Yeah, okay, that I see what you mean. Need to explicitly use the bound x to the n minus 1 plus x to the n minus 2 plus is less than or equal to nm to the n minus 1 via the triangle inequality. X to the c shouldn't be gear. Step x x minus x. Oh. I mean, isn't it? Is that not a true statement? Oops. X and C are in very similar places on my keyboard layout. We assumed epsilon's greater than 0, so that's true. It does logically follow. Is only valid if you have established that the sum is less than or equal to the sum is less than or equal to this using the triangle inequality. That's what you mean, right? True. Alright, I'm gonna go eat lunch, I guess, assuming that that's fine enough. And I'm gonna start streaming again in like an hour, because I still have to do more of this fucking shit. Probably record a video about this setup too, because